Welcome back. This will be part B, or the second part, of a video lecture on section 3.5 covering subspaces, basis, dimension, and rank. In part A, we talked about subspace and subspaces associated with matrices. In this second part, we'll discuss basis. So let's begin with a discussion of what is a basis. A basis for a subspace S of Rn is a set of vectors in S that spans S and is linearly independent. So there are two requirements on this collection of vectors for it to be a basis. It has to span the subspace and it has to be a linearly independent collection. So let's take a look at this note I have here below. Let's imagine that script B is a basis for some subspace S. So script B has to satisfy a spanning requirement. So using B, we can build a bridge to any element of S. Any element of S can be formed as a linear combination of the vectors in B. But that collection must also be independent. So the elements of B, in some sense, are all necessary. If we eliminate any member of B, then we can no longer span all of S. Now, to get comfortable with this idea of a basis, let's work the following problem. So, find a basis for the span of the collection of vectors shown below. Let's go to the document camera and I will show you how we can proceed to find a basis for the span of this collection. All right, welcome to the document camera. Let's take a look at the solution to this problem. Now, in this problem, we've been given four vectors in R4, and we're looking at the span of those four vectors. That's going to be some subspace in R4, which I'll identify as S. And this problem asks us to produce a basis for S. So that's a spanning set that is linearly independent. All right, now let me show you a method that's always going to work to solve a problem of this type. I'm going to take these vectors, which have been given to me as columns, and I'm going to turn them into rows and feed them into a matrix row by row. So I've simply taken these four columns and made them the successive rows of this matrix, and I'll call that matrix A. So the first observation is that this set S can be thought of as the row space of the matrix A. Okay, now the next thing to do is to row reduce this matrix A. We're going to take it all the way down to its reduced row echelon form. So I will spare you the details, but there's a sequence of elementary row operations that we can do that will take this matrix down to 1, 2, 0, negative 2. That's row 1. 0, 0, 1, negative 1. That's row 2. And it turns out that the last two rows consist entirely of zeros. So we'll call this matrix A star. That's the reduced row echelon form of A. Now, let's see what the theory tells us. Theorem 3.20 tells us that the space S that we're interested in, which is, in fact, the row space of A, is also equal to the row space of A star. So the thing that's bridging this here for us is theorem 3.20. All right, that's a very important piece of this puzzle, that after I do the sequence of row operations, the row space of this reduced row echelon form is the same as the row space of the original matrix. Okay, so that's an important part of this. Now, here's another important observation. When I look at A star, two of its rows consist entirely of zeros, and they are not going to contribute to the span. So in fact, the row space of A star is simply spanned by its non-zero rows. So this is equal to the span of just its non-zero rows, and I can re-represent those as columns to bring it back to its original context. And this is already an improvement, right? Because it says these two vectors alone span as much as these four vectors did, right? I can create the same subspace of R4 by using these two vectors as I did by using these four vectors. Now that doesn't tell us that this is a basis. We still have to show that these vectors are linearly independent to claim that this is a basis. But we're well on our way. We've already made an improvement. Okay, now we have to show that these two vectors form a basis. And now let me show you why that's, through this method, why that's always going to be easy. Now, in order to check the independence, I have to look at a linear combination of these two vectors, and I have to set that equal to the zero vector, and I have to see if there are any non-trivial solutions. So I'm going to take A times this vector, and B times this vector. And I'm going to set that equal to the zero vector. All right, and I'm going to see what kind of solutions there are to this equation. Now, I claim that there's only two of these rows that matter. Everything's going to be revealed already by two of these rows. And these rows correspond to the positions of these leading ones in our reduced row echelon form. So when I take these rows and reinterpret them as columns, right, this first row is going to tell me something interesting, and this third row is going to tell me something interesting because these are the positions that correspond to those leading ones. So I'm going to find something very telling in this first row, and I'll find something very telling in this third row. Let's take a look. In this first row, we're getting 1 times A plus 0 times B equals 0. And in this third row, we're getting 0 times A plus 1 times B equals 0. Well, this first equation tells me that A is equal to 0. And the second equation tells me that B is equal to 0. And so I know that the only solutions to this equation correspond to the choice of A and B both equal to 0, and we call that the trivial solution. So the only solution to this equation is the trivial solution, and that means that these vectors are in fact independent. Okay? Since these vectors are independent and they span our space S, the collection of vectors B consisting of these two vectors B is a basis for S. The solution to our previous problem reveals the following method. And I'll call this the row method for finding a basis. So let S be the span of some vectors u1 through un. To find a basis for S, let's let A be the matrix with rows u1 through un. Next, we'll find A star, which is just the reduced row echelon form of A. The non-zero rows of A star form a basis for S. So this is one way for finding the basis for a span of a collection of vectors. We simply put the vectors in as the rows, we row reduce, we throw away all the rows that consist entirely of zeros, and the rows that remain must be a basis for the subspace S. Let's work another problem of this type. In this problem, let S be the span of these four vectors from R2. Let's find a basis for S. Now I want to show you a technique that is different from the one we just did. This one we're going to work with these as directly as columns. So let's go to the document camera and investigate that method. Welcome to the document camera. In this problem, we've been given four vectors in R2. We formed the span of that collection of vectors, and that's going to give us a subspace, let's call it S, of R2. And our goal here is to find a basis for S. That is a linearly independent spanning set for the subspace S. Now, I've given these vectors names U1 through U4. Now, I'm going to show you a very different method from what we did before in our previous problem. The previous problem is very much like this, but I'm going to show you a very different method. And in this method, basically what we're going to try to do is take these vectors and try to discover some dependencies amongst them and try to eliminate some of them and keep only the ones that will form a linearly independent subcollection. So we're essentially trying to find a method to go in and take some of them out because they're in some sense redundant. Okay, now the beginning of this, we begin by looking at the homogeneous equation C1 times U1 plus C2 times U2 plus C3 times U3 plus C4 times U4 equals the zero vector. So we're going to begin looking for possible solutions to this homogeneous system of equations. Now we know that this can be presented as an augmented matrix where I simply feed these vectors in as the columns. And the column of constants here will correspond to this zero vector. Now, when we row reduce this matrix, we're going to perform a sequence of elementary row operations. We're going to row reduce this matrix. Here's what we discover. We're going to get a 1, a -2, a 0, and a -2, and that'll be complemented by a 0 on this side, and then we'll have a 0, a 0, a 1, and a 1, and a 0. Now here's what the method is going to say. I'll give you the, I'll cut to the chase here, right? The columns that have the leading ones, so this first column and the second column, it turns out that the corresponding vectors will be a linearly independent collection that spans the space S. So in other words, what this is showing us, and I'll show you why, what this is showing us is that the vector that corresponds to column 4, U4, and the vector that corresponds to column 2, namely U2, that these two vectors are redundant, that in some sense we can go in and eliminate them. The remaining two vectors will still span the same space and they will be linearly independent. So this method is basically saying take the columns, put them in, row reduce, keep the vectors that correspond to the leading ones, and that will form a basis for the space S. Now, let's see if we can understand why this method works, okay? Now let's remember that these columns correspond to these coefficients C1, C2, C3, and C4. So let's write out what these equations are telling us. The second equation is telling us that C3 plus C4 is equal to 0. And the first equation is telling us that C1 minus 2C2 minus 2C4 is equal to 0. Now let's solve for C1 and C3 in terms of C2 and C4. So C3 is equal to negative C4, and C1 is equal to 2C2 plus 2C4. So that's what we're getting. All right, when we look at the equations that are here in this reduced row echelon form. Now, let me show you how we can use this in two different ways to eliminate. I can show you why we can eliminate U2 and U4 based on these equations. So, first, what I want to do is I want to set C4 equal to 1. And I want to set C2 equal to 0. All right. This is going to allow me to concentrate on this vector U4. I'm going to set C4 equal to 1. I'm going to set C2 equal to 0, and I'm going to show you how U4 can be expressed in terms of U1 and U3. So let's check our equations here. If C2 is equal to 0 and C4 is equal to 1, we can see that C3 will be negative 1. And C1 will be equal to 2. Okay? Now, if we go back to our original equation, this is telling me that 2 times U1 plus 0 times U2 plus negative 1 times U3 plus 1 times U4 is equal to 0. Now let's solve this equation. Let's keep U4 on this side. Let's move everything else to the other side. So let's solve this for the vector U4. So this is saying U4 can be expressed as a negative 2 times U1 plus a 1 times U3. All right? So this says that U4 is actually expressible in terms of U1 and U3. Now we should check that. Is it the case that if I scale this one by negative 2 and then add on U3, do we get U4? So I multiply by negative 2, that's negative 2, plus 2 is 0, that's true. When I multiply by negative 2, that becomes 4. 4 plus a negative 1 is 3. So in fact, we have discovered that U4 can be represented by U1 and U3. And what this means is that this vector, in terms of the spanning problem, this vector is redundant. It's not adding anything to the mix that couldn't have already been handled by U1 and U3. U1 and U3 together can do the work of U4. And so this relationship here is telling me that in terms of spanning, this vector is redundant. It's not necessary. It's not doing anything that can't already be done by these two. All right, now let's show that U2 is also redundant. So kind of imitating what I did here, I want to switch the roles of these. I want to now let C2 equal 1 and C4 equal to 0. Okay, now let's look at what falls out of that. Well, C3 is going to be the negative of C4, so that's going to be 0. And C1 is going to be 2 times C2 plus 2 times C4, so that's just going to be 2. All right, so what comes out of this is that 2 times U1 plus 1 times U2 plus 0 times U3 plus 0 times U4 must be the 0 vector. And remember, I want to show something about U2, so I'm going to write U2 in terms of U1. U2 is a negative 2 times U1. That's what we've discovered. Now, we should check that. If I take U2, is it the same as multiplying U1 by negative 2? So I'll get a negative 2 there, and I'll get a 4 there. So in fact, that relationship is true. Now, what this is telling me is that in terms of the spanning problem, U2 is already, all the work of U2 can be done by U1. So this vector is also unnecessary in terms of the spanning problem. So what we've shown through this extended argument is that by studying this homogeneous system, we can show that some of these vectors are rather unnecessary. They're not helping in the spanning problem, that U1 and U3 already can do all of the work as the entire collection U1 through U4. All right, now that doesn't show that what's left is a basis. It just shows us that S is the span of U1 and U3. We would still have to show that these vectors are linearly independent. Now, I'll show you how we've already done all the work we need to do. We just we may not realize it yet, but let's study the independence question now. Let's see if these vectors are independent. Now let me get a fresh start on this. How do I test for independence? Well, I'd have to look to see whether or not there are any non-trivial solutions to this equation. And how can I study this equation? I can study it as an augmented matrix where I feed in U1, U3, and a column of zeros. Now I'm going to row reduce this matrix. And I will show you the answer, but I'm going to show you the answer, but I'll show you that we already knew this. It row reduces to this. Okay, and if we read this, remember the columns are A and B. It says A is equal to 0 and B is equal to 0. Okay, and that means that the only solution to this equation is the trivial solution where both A and B are equal to 0. And so that does say that these vectors are independent. And so the long and short of this is that these two vectors alone will form a basis for S. All right, now let me show you why we didn't actually have to do this end game. Let me show you why we already had all the information we needed. All right, now in this end game, we're taking this augmented system where I feed U1 into column 1 and U3 into column 2. Now, that's no different than if I started with my original system and I basically just ignored what was happening in column 2 and column 4. That's essentially the same matrix. All right, just ignore column 2 and column 4. When I do all my row steps, that's going to be equivalent to eliminating column 2 and column 4. And so I already had this row reduction above here. When I did that original row reduction, I already had buried inside of it the row reduction that would just involve columns 1 and columns 3. Okay? That was already there. All that work was already there. So I already knew that those columns contained leading ones, and therefore the solution to this homogeneous equation was going to be the trivial solution. Okay? So if we just step back and look at this method, what does it say? It says, when you're given a collection of vectors and you're studying the span of that collection of vectors and you want to extract a basis, all you have to do is take these vectors, put them into a matrix, row reduce that matrix, and keep only those vectors that correspond to the columns containing the leading ones. In this case, it was column 1 and column 3, so I keep the vectors U1 and U3. We can show, we don't have to show this every time, but each and every time we could show that the vectors that don't have leading ones can be eliminated because they are, in a sense, redundant. Okay, so this is a very different method from the method that we did before, where we fed these vectors in as rows and did row reduction. Here we keep the vectors as columns and do row reduction, and we have a slightly different interpretation of the end game. Now, let me show you one way that this method is very different than the method that we did before. If we study this method, the basis that we're ending up with is a basis that consists of some of the original vectors. In other words, we're showing that the basis for this space S consists of 2 of the original vectors, and we've eliminated 2 of them. But the basis is consisting of a subset of the original set of vectors. If you look at our other method, we get a completely different set of vectors that form our basis. In some sense, it is not a subset of the original collection that we started with. So this method will always eliminate some and keep some of the original collection. And so it has that feature. All right, let's take a look at this method in kind of a general form. Now let's try to extract from our previous solution a method, and I'm going to call this method the column method for finding a basis. So let S be the span of the vectors u1 through un. Our goal is to find a basis for S. So in the column method, we're going to let A be the matrix with columns u1 through un. Next, we're going to find the reduced row echelon form of A. Let's call that matrix A star. Now the columns of A that correspond to the columns of A star that contain leading ones form a basis for S. So at this point, we've got two different methods for solving essentially the same problem. In this problem, we want to extract a basis for a span of a collection of vectors. And so we have a row method and we have a column method, and they are similar in some respects and they are different in some respects. I think one way to see the difference between these methods is to put them side by side. So in this example, I've got three vectors in R3, a vector I'm calling u1, a vector I'm calling u2, and a vector I'm calling u3. S is going to be the span of this collection, u1, u2, and u3. Now we want to find a basis for S. Now by the row method, we feed these vectors in as the rows of a matrix, and we proceed to put the matrix into its so-called reduced row echelon form. We notice that there's a row of zeros at the bottom, and so we just throw that row away. The rows that remain are a basis for the span of u1, u2, and u3. So these two vectors, the vector 1, 0, negative 3, and the vector 0, 1, negative 2, are a basis for this space S. Okay, that's the row method. By the column method, I take the same vectors u1, u2, and u3, but this time I insert them into the matrix as columns, as the columns of A. I row reduce the matrix and get its reduced row echelon form. Now in this case, I interpret the answer differently. I look for the columns that contain leading ones, in this case column 1 and column 2. Then I go back to the original matrix and I say, therefore, column 1, vector u1, and column 2, vector u2, form a basis for S. Okay, so that's the row method and the column method side by side. Hopefully by seeing them on the same page, you can appreciate how they are similar to each other, but how they are different from each other. Now I want to close this section on basis by solving one more basis problem. Let A be the matrix that you see here with 2 rows and 5 columns. I want to find a basis for the null space of A. So join me at the document camera for the solution to that problem. Welcome to the document camera. We've been given a matrix A with 2 rows and 5 columns, and we've been asked to find a basis for the null space of this matrix. Now we know that the null space of the matrix corresponds to the solution set to this homogeneous equation. And so as before, we begin with the augmented matrix, where we take this A as our matrix of coefficients and we augment it with a column of zeros. And we think of the variables, let's say, as x1 through x5. So we're trying to describe the solution set to this homogeneous system. Now, when you row reduce this matrix to explore its solution set, here's what we find. So a sequence of row operations will reveal this reduced row echelon form. We're going to have 1, negative 2, negative 1, 0, negative 4, 0. That's the first row. And then the second row becomes 0, 0, 0, 1, negative 2, and 0. So we have 2 leading entries, 2 leading ones, here and here, and those are going to correspond to bound variables. That would be x1, x2, x3, x4, x5. So we're going to have bound variables in x1 and x4, and x2, x3, and x5 will be free variables. Now, we can explore the relationships between these variables by examining these equations. So this equation tells me, for example, that x4 minus 2x5 is equal to 0. Or x4 is equal to twice x5. My first equation tells me that x1 minus 2x2 minus x3 minus 4x5 is equal to 0. And so solving for this bound variable, I can see that x1 is twice x2 plus x3 plus 4x5. Now, when we try to describe the solution set to this homogeneous equation, we have to realize that these free variables can take on any value that they want, and so we'll have to record that carefully. So when we have a description of the solution set, since x2 is one of our free variables, it can take on an arbitrary value, let's say r. x3 is free, so it can take on an arbitrary value s. And x5 is free, so it can take on some arbitrary value t. But our bound variables, x1 and x4, will be described in terms of them. So x4 is twice x5, so it'll be twice t. And x1 is going to be 2 times r plus s plus 4t. So any solution to this system of equations will follow this pattern where r, s, and t can be arbitrary. All right, now if we want to write this in vector form, we'll have first entries and second entries, third entry, fourth entry, and fifth entry. And then we can do as before. We can split this out into a vector that's being scaled by r, a vector that's being scaled by s, and another vector that's being scaled by t. I have an r in my first component, so there'll be a 2 in that position. There's an r in my second component, but there's not an r in any of the remaining components. So that'll be the vector that's being scaled by r. I will do the same for s. I'm seeing an s there, so there's a 1 in that position, a 0 in component 2, a 1 in component 3, and then a 0 and 0. And then finally for t, we're seeing a 4, a 0, a 0, a 2, and a 1. Okay, now already we've shown that these three vectors are a spanning set. For the null space of A. In other words, anything that satisfies the homogeneous system, think of that as this vector x, it can be written as a linear combination of these three vectors. So we've already got a spanning set. Now we need to argue that this collection is linearly independent, and that will give us a basis. Now let's think about what the linear independence question is getting at. And now let me temporarily call these vectors u1, u2, and u3. We have to show that u1, u2, and u3 are linearly independent, since we have to examine this equation and see if it has any non-trivial solutions. Now I'm going to show you that it will not, and anytime you use this method, you're going to produce not only a spanning set, but you'll always produce a linearly independent set. So this method is always going to produce a basis not just a spanning set, but a basis. So let's see why is this collection of vectors linearly independent? And what I want us to concentrate on is 3 different rows of this vector, this collection of vectors, okay? And I want us to concentrate on exactly the rows that correspond to these columns that contain the free variables. So in this case, we have column 2, column 3, and column 5. Let's look at row 2, row 3, and row 5 in this equation. So if I take this vector u1 and I multiply by a in row 2, I'm going to get a. I'm going to have b multiplying 0. And I'll have c multiplying 0. And that shows us that a is equal to 0. Okay? If I look at row 3, I'm going to have a multiplying 0. I'm going to have b multiplying 1. And I'm going to have c multiplying 0. And that shows that b is equal to 0. And finally, if I look at row 5, which corresponds to this last free variable, I'm going to have a multiplying 0, b multiplying 0, and c multiplying 1. And that has to be equal to 0, so c is equal to 0. So I'm claiming that anytime you use this method and you produce this linearly independent set, the same procedure here will also show that the vectors that you've produced are linearly independent. And so not only is this a spanning set for the null space, it's actually a basis for the null space. Now let's summarize the findings in our previous problem. So let's think of the general problem of finding a basis for the null space of a matrix. So let a matrix A be given. In our first step, we find A star, the reduced row echelon form of A. In the second step, we solve the homogeneous system where we take A star and augment it with a column of zeros, and we express the bound variables in terms of the free variables. In step 3, we show that any solution of the original homogeneous equation ax equals 0 can be expressed as a linear combination of vectors, one for each free variable. This collection is linearly independent and hence forms a basis for the null space of A.